Next, one more example for exhaustive search is called as knapsack problem. In the knapsack problem, we are given n items, and the items of each, the weights of each item is actually W1, W2, W3, like up to Wn. And the value or the price of each item, n items, are nothing but V1, V2, V3 up to Vn. Now, when the knapsack capacity is given, called as capital W. Now we have to find out the most valuable subsets of items that fit into the knapsack. That means we have to pick some of the items from this here. Okay, we have to pick some of the items. N number of items are given. In that n number of items, I have to pick some items whose total weight should be less than this knapsack capacity. But when you calculate the total value, it should be more than any other subset of items. Such problems can be solved using exhaustive search or brute force technique. In the exhaustive search approach, to do this, in the exhaustive search approach, to this problem leads to generating, in the exhaustive search approach, to do this problem leads to generate all the subsets of the sets of n items, computing the total weight of each subset in order to identify feasible subsets, the ones with the total weight not exceeding the knapsack capacity, and finding the subset of the largest value among them. That means, in exhaustive search, first we have to identify all the different subsets of the n items. For each subset, we have to compute the total weight. If the total weight is exceeded the knapsack capacity, we just eliminate such subsets. That means we are interested in only that subsets whose weight is less than the knapsack capacity. The weights of that subsets are actually calculated here. After that one, we have to total the weights of each subset. We have to identify the weights of each subset's total weight. Then we have to find the subset which has the largest value. The value should be very large, but the total weight should be less than the knapsack capacity. Such element I have to identify. That is called as knapsack problem. Now consider this example here. Our knapsack size is 10 and we are here given n number of items, and these n number of items are having some weight and value. The item 1 having a weight of 7, whereas it is having a value of 42. Item 2 has a weight of 3 and have a value of 12. Item 3 has a weight of 4 and value of 40. In similar way, I have one more item called as item 4, whose weight is 5 and value is 25. I have totally 4 number of items, so it will create totally 16 subsets. That is 2 raised to 4. If n number of items are given, it will create totally 2 raised to n subsets. Since here it is given 4 items, it will create totally 16 subsets. Okay, from 0 to up to 1, 2, 3, 4. First I will pick the each and a single element, then I will pick the 2 elements, then 3 elements, then 4 elements, like this way. Then I will identify the total weight. The first item's weight is actually 42. Sorry, so first item's weight is 7 here, is to written here, and value is 42. Like that I have written individual weight and value. Then I will take the item 1 and 2, this and this. Then I will take the item 1 and 2, identify its weight, 7 plus 3, 7 plus 3 is nothing but 10 here. 7 plus 3 is nothing but 10. Okay, 10 is actually a feasible solution because it is same as knapsack capacity. So I will take the value of this here, 42 plus 12 is nothing but 54 here. Total the value of these two and return 54. Then I will take one more element, 1 and 3, 1 and 3. I will calculate the weight. Weight is 11. 11 means it is more than capacity. So I will just skip this value here. I have to pick only that value which having the weight, total weight less than 10 or equal to 10. Okay, like that I have computed for each and every combination, like 2 and 3, 2 and 4. Okay, 2 and 3 and 4. I will find the weight like 7, 8, 9, and these are the total values. If you go to here 2 and 3, now see 2 and 3 is nothing but here 3 plus 4 is nothing but 7 here weight is, and the total value is 12 plus 40 is nothing but 52. Like that for each combination or each subset I have to calculate the total value. If the weight is more than 10, I have to just skip that total value because it's not the solution. Then within this total value I have to pick the value which is very largest value, that is nothing but 65 here. If you compare all the elements here, this is the largest value, and this is our optimal solution. Here the weight is 9 and the value is 65. This is the optimal solution for our knapsack problem. In knapsack problem, the number of subsets of n elements, that is 2 raised to n. As I already told, okay, if you have n number of items, we have totally 2 raised to n number of subsets. So our exhaustive search leads to big omega 2 raised to n algorithm. The order of growth of this knapsack problem is 2 raised to n. That is exponential problem. Our travel and salesman problem is actually factorial problem, and this knapsack problem is actually exponential problem. Okay, in knapsack and traveling salesman problem, each element of the problem's domain has to be searched for obtaining solution. So such problems are also called as NP hard problems. The both knapsack and traveling salesman problems are called as NP hard problems.